Say Betelgeuse 3 times and a ghost appears, at least in the movies. But 650 light-years away, a bloated, dying star sharing almost the same name is preparing something no special effect could match. When Betelgeuse finally detonates, it won't need an invitation. It'll shine in broad daylight, possibly brighter than the full moon. And here's the truly strange part. It might have already exploded. The light just hasn't reached us yet. Look at the constellation Orion on a winter night, and Betelgeuse is impossible to miss, a red-orange dot marking the hunter's shoulder. But calling it a dot is absurd understatement. If Betelgeuse sat where the Sun is now, its surface would extend past Mars, past Jupiter. It would swallow everything out to somewhere between Jupiter and Saturn's orbits. This is a star so enormous, so bloated, so unstable, it's basically a bomb waiting for its own trigger. Unlike the Betelgeuse in Tim Burton's films, this one needs no summoning spell. In late 2019, astronomers noticed something alarming. Betelgeuse was dimming. Not subtly, it dropped to about 40% of its normal brightness over just a few months. Headlines erupted. Was the star about to explode? Were we about to witness a supernova in real time? The truth turned out to be less dramatic, but strangely more revealing. A massive plume of hot gas had erupted from Betelgeuse's surface. As it moved away and cooled, it condensed into dust. That dust drifting between us and the star blocked the light, just a shadow. But that word hides something important. Betelgeuse is violently unstable, shedding mass, convulsing. These are the symptoms of a star in its final act. The fate of every star is written in its core. Our Sun fuses hydrogen into helium, releasing energy that keeps it inflated against its own crushing gravity. It's been doing this for 4.5 billion years and has about 5 billion more to go. Betelgeuse burned through its hydrogen long ago. It's now fusing heavier and heavier elements, helium becoming carbon, carbon becoming oxygen, oxygen becoming neon, then silicon. Each stage burns faster, hotter, more desperate. If hydrogen burning is a slow candle, silicon burning is a camera flash. When a star's core starts fusing silicon into iron, it has roughly a day left to live. Iron is where fusion stops paying dividends. Every element up to iron releases energy when fused. Iron absorbs it. The moment a star's core becomes iron, it's built a trap for itself. Fusion shuts down. Outward pressure vanishes, and gravity, which has waited patiently for millions of years, wins in a single second. The core collapses at 70,000 kilometers per second, nearly a quarter of the speed of light. Material that moments before was larger than Earth crushes down to a sphere about 20 kilometers across. The density becomes so extreme that protons and electrons are forced together into neutrons. What remains is a neutron star, a city-sized object weighing more than the Sun. But the outer layers don't know the core has collapsed. They're still falling inward. When they slam into the incompressible neutron star surface, they bounce hard. A shockwave rips outward through the star at 10,000 kilometers per second. Within hours, it reaches the surface, and then Betelgeuse, for the first and last time, truly announces itself. Here's a quick calculation. Betelgeuse sits about 650 light-years away. A typical Type II supernova releases roughly 10 to the 43 joules of light energy. That's a 1 followed by 43 zeros. Spread over 650 light-years of distance, what reaches Earth? Work through the inverse square law, convert to apparent magnitude, and you get roughly -12. For comparison, the full moon sits at about -12.7. A supernova Betelgeuse would rival the full moon's brightness, compressed into a single searing point, visible in broad daylight, casting shadows at night for weeks. No séance required, no saying the name 3 times, just looking up. Humanity has witnessed this before. In 1054, Chinese astronomers recorded a guest star so bright it remained visible during the day for 23 days. At night, it persisted for nearly 2 years. Today, at that exact position, we see the Crab Nebula, the expanding debris of that ancient explosion, with a rapidly spinning neutron star still blinking at its heart. The last supernova visible to the naked eye in our galaxy was Kepler's supernova in 1604. Johannes Kepler himself studied it. Galileo had just built his first telescope. Since then, nothing. 4 centuries of silence. But this time, something will see it coming. Not because astronomers will watch Betelgeuse dim or flicker, but because of ghost particles that arrive before the light, neutrinos. During a core collapse, roughly 99% of the energy escapes not as photons, but as neutrinos. These particles interact so weakly with matter that they stream straight through the collapsing star while light is still fighting through the outer layers. When Betelgeuse explodes, detectors like Super Kamiokande in Japan and Ice Cube beneath Antarctic ice will ring like alarm bells hours before any telescope registers anything unusual. The universe offers advance warning if you know how to listen. So when does Betelgeuse go? Here's where the star and its cinematic namesake diverge completely. In Betelgeuse, you control when the chaos arrives. You summon it. But Betelgeuse operates on no human schedule. Estimates place the star somewhere between a few tens of thousands and 100,000 years from detonation. On cosmic timescales, that's imminent. On human timescales, it could mean tomorrow or long after everything we've built has crumbled. The light reaching Earth tonight left Betelgeuse around 1375. If the star exploded any time between then and now, we simply don't know yet. The news is still traveling. When that news finally arrives, whether next year or in centuries, the remnant will reveal something profound. If the collapsed core weighs below roughly 2.5 solar masses, it stabilizes as a neutron star. If heavier, even neutron degeneracy pressure fails. The core keeps falling and becomes a black hole. Betelgeuse sits frustratingly close to that boundary. Every supernova we catch adds 1 data point to understanding exactly where that threshold lies. In the films, Betelgeuse is chaotic, theatrical, and arrives on command. The real Betelgeuse matches 2 of those. It's chaotic, convulsing, shedding mass, burning fuel at a frantic pace. It's theatrical. When it finally goes, it'll be among the brightest celestial events in recorded history. But it won't arrive on command. It doesn't care whether anyone is watching. It doesn't require its name spoken 3 times or even once. Somewhere in the winter sky, a star's core is silently burning through its last reserves of fuel. And for the first time in 400 years, humanity has instruments positioned at the edge of detection, waiting to catch the first whisper of a giant's death. The only real question is whether we'll be lucky enough to be watching when the light finally reaches us. If this was interesting, hit the subscribe for more and turn that notification bell on.